All right. So before we talk about lesson 5.3, which is the special centers of triangles, I just want to talk to you about um, the lines that can be made inside of a triangle. So the first type of line that you have is a perpendicular bisector. And you can recognize a perpendicular bisector because, first of all, you'll see that it's perpendicular. The line that's drawn is perpendicular to a side. It's perpendicular to a side. But it also bisects. It also bisects that side, meaning that it cuts the side of a triangle into two congruent pieces. Cuts the side of a triangle into two congruent pieces. If you have three perpendicular bisectors, so if we were to try and draw, like if I were to imagine that this was the middle of this line segment, and I were to try and draw a perpendicular to this line right here, and then if I found the midpoint of this side and drew a line perpendicular this way, I would see that the point that all three of those lines, the point that all three of those perpendicular bisectors, excuse me, intersect is called the circumcenter. The circumcenter has some unique features. All right. It's equidistant from the vertices, meaning that if I were to draw a line from the center, this is the circumcenter, the point where all three lines intersect. If I were to draw a line from the circumcenter to any vertice, from the circumcenter to any vertice, this line segment that I draw from this circumcenter to any vertex would be the same distance, meaning that they're equidistant. So that's what this says. A circumcenter is equidistant from the vertices of the triangle. Why? Well, you'll notice that the circumcenter is the center of a circumcircle, meaning that you can draw a circle around the triangle. You're essentially circumscribing about the triangle. And these distances from the circumcenter to the vertex of the triangle actually become the triangle's radii. Sorry, they become the circle's radii. All right. So the next special segment that we're going to talk about is an angle bisector. Now, how do you recognize an angle bisector? Well, first of all, the segment bisects the angle. So the segment is going to has nothing to do with the opposite side. It's just bisecting the angle. So I'm just cutting this angle into two congruent pieces. So I'm going to bisect this angle, cut this angle into two congruent pieces. And I'm going to do the same thing. Well, that was awful. I'm going to do the same thing here. Cut this angle into two congruent pieces. And when I draw three angle bisectors, the place where those three lines intersect or become concurrent is called the incenter. Now, the incenter is unique because you can inscribe a circle inside of a triangle. So, as you can guess, the incenter is equidistant from the sides of the triangle. So the incenter is equidistant from the sides of a triangle. The incenter is made by three angle bisectors. It's the point of concurrency of three angle bisectors. Then this third line that we have is a median. A median goes from the midpoint of a side to the vertex. So you just find the midpoint and then draw a line to the vertex. Midpoint, draw it up to the vertex. Sorry, I'm just trying here. To the vertex. A midpoint and draw it up to the vertex. So if I had drawn these nicer, the place where those three medians intersect is called the centroid. Now the centroid has some unique features also. The centroid is 2/3 the length of the whole segment from the vertex, or 1/3 to the opposite side. So the other way to think about this is that this segment right here is half, sorry, this segment right here is 2 times this segment, or this segment is half of the longer one. And then lastly is an altitude. An altitude is the same thing as height. So we go from the vertex to the opposite side, drawing a perpendicular. Remember, height is always perpendicular. So from the vertex to the opposite side, perpendicular. From the vertex to the opposite side, perpendicular. The place where these intersect is called the orthocenter. And the orthocenter has no specific properties that we're going to talk about at this time. All right. So now we're going to look at the centers of our triangle and we're going to identify them. So I have a circumcenter. So let's talk about the segments that I can see inside of my triangle. So let's see. I see that these two sides are broken up into two congruent pieces. Two congruent pieces. Two congruent pieces. And I have a perpendicular. So these are created by perpendicular. That's the symbol for perpendicular bisectors. They're created by perpendicular bisectors. So what are the important facts? Well, the circumcenter. Oh my goodness, I don't have a working stylus at home, sorry. So the circumcenter is equidistant from each side of the triangle. The circumcenter is equidistant from not from each side, from each vertex. Because remember, we circumscribe. So these actually become the radius of the circle. So it's from the vertex. All right. When I look at this next triangle, I know it's the incenter, and I recognize it because these are angle bisectors. The only thing that I'm being told about them is that I'm bisecting an angle. This angle right here is broken into two congruent pieces. This angle is broken into two congruent pieces. So these are created by angle bisectors. All right. And the incenter is equidistant from each side of the triangle. Equidistant from each side of the triangle. Okay. I'm going to actually go back to the circumcenter for a second. So if the circumcenter is equidistant from the vertex, what can we say? Well, we can say that segment AM, actually, I'm not even, we can say the distance from A to M is equal to the distance from C to M is equal to the distance from B to M. And when I look at the incenter, and I talk about the incenter being equidistant from each side of the triangle, that means that MX is equal to MY is equal to MZ. Alrighty. Now I have the centroid, and the centroid, remember, just takes the median. So I see that my triangle sides are broken into two congruent pieces. That's a midpoint, and it goes to the vertex. That's what a median does, the midpoint to a vertex. So this is created by the medians of a triangle, and a centroid is created by a vertex that is connected to the midpoint of the opposite side. So remember, there are some special things. So I'm just going to use this segment right here. I'm going to use this segment right here to talk about it. So I know that um, BM equals 2/3 of the whole segment, BZ. I know that MZ is 1/3 of the whole segment, BZ. But I also know that MZ is half of BM, or BM is twice MZ. Now, that works for all of the medians. It can be broken down like that. All right. Our last one is the orthocenter. Remember that the orthocenter is made by altitudes. You just go from the vertex to the opposite side and it's perpendicular. An altitude is a height. An altitude is a height. Okay. So an orthocenter is created by a vertex connected to the opposite side so that it is perpendicular to that opposite side. And this upside down capital T is the symbol for perpendicular. All right, so those are the special sides. So we have perpendicular bisectors, angle bisectors, medians, and altitudes. And those special segments within a triangle create special points of concurrency known as circumcenters, incenters, centroids, and orthocenters. So after you fill out your graphic organizer, you're going to work on the activity on pages 11 and 12. It's a GeoGebra discovery activity, and I'm going to make a short video of how you can actually interact with that, show you how you can click and unclick special features.